Okay, so this is a video on the reverse chain rule. So there's two versions of reverse chain rule. We have this version where you've got a fraction, so k f dash x over f of x, respect to x, it's a fraction, and then you've got this version where you've got k f dash x f x to the power of n dx. And in both cases, the constant k is called the adjustment constant. We'll talk about that in a bit more detail. Okay, so get rid of that. So this first question, obviously we've got the version where it's the integral of k f dash x fx to the power of n with respect to x. Okay, now clearly in this question, so you see our function f of x is just the 1 plus cot of x. Okay, now always a good idea to just do f dash x straight away. Now, clearly in this case, we could show it using the quotient rule, but it should know it's minus cos x squared x. So that constant one will just disappear, wouldn't it? Okay. Now, the way this works, okay, so we're always thinking about what our integral going back to what we started with. Okay, so we know it's to the power of 3, so we know our integral must contain this. It must contain 1 plus cot x, okay, to the power of 4. So all I've done is added 1 to the power of 3, obviously. And what we're doing, what's called reverse chain rule, we think about what we get back to, and what we need to start with, rather, if we differentiate that function. Now, we know, and differentiate, the power comes out, so the 4 comes out. The bracket obviously differentiates to minus cosec squared x, okay? And then we've obviously left with the bracket, but we're not 1 off the power, so 1 plus cot x to the power of 3. Now, you can clearly see that's very, very similar to what we started with. Okay, the only difference is obviously what we've got is we've got minus 4 cosec squared x. We'll talk about that in a minute. Now, what we know is if we have this function, this is the important bit, I know that if I start with this function, why it's called reverse chain rule, if I integrate this, okay, going the other way, I will end up with my 1 plus cot x to the power of 4. So I need that to begin with. Does that make sense? So the important thing here is the minus, you've got minus 4 cosec squared. Highlight that as well, brother. You've got 1 there. So this is where the adjustment constant comes into play now. Can you see? Because you know you have to have that minus 4 cosec squared for it to work. Okay, so where it comes in is we write the integral. So we just write our minus 4 cosec squared x. Theta. 1 plus cot x to the power of 3. Okay, because that minus 4, I obviously need a minus a quarter to come out. So we always bring the k outside the integral. Okay, because minus quarter times minus 4 would just give you 1. So you get 1 cosec squared x, which I've got originally. Does that make sense? The really important thing, this whole integral, this is the same, can't be different as that. Okay, and we know our minus 4 cosec squared 1 plus cot to the power of 3 is going to integrate to our 1 plus cot to the power of 4. So this integral will simply now be, so it makes it really easy, this will now be just minus a quarter, 1 plus cot x to the power of 4. Make it a bit neater for you. Yeah. Between a limit of, 45 degrees pi over 4 and 30 degrees pi over 6. So that's what our integral will be. Let's make that 4 look a bit neat. Okay, well, here, what we've got is 45 degrees. So we now tan 45, we should know it's 1. So cot 45 is going to be 1. So 1 plus 1 is 2. 2 to the power of 4 is 16. 16 divided by minus 4 is just minus 4. So our first limit is minus 4. Our second limit, tan 30 is 1 over root 3. Therefore, cot 30 is going to be root 3. So you're going to have minus a quarter, 1 plus root 3 to the power of 4. So you've obviously got to try and work out what that is. Okay, that's what it will be. Okay, makes sense, that one. Right, so I need to get some room now. Okay. Let's get some room on each. Hopefully it's making sense. Right, okay, so it's got to deal with this now. What this is going to be. Okay, so I've clearly got -4 plus a quarter. Yeah, and we've essentially got 1 plus √3, 1 plus √3, 1 plus √3, 1 plus √3, and just do it in pairs. Okay, so we know this is going to be 1 plus 2 √3 plus 3, which is 4 plus 2 √3. Yeah, so obviously it's going to be the same. Yeah, it's the bracket that I'm going to go times by a quarter at the end. So if we expand this one, 4 lots of that, you get 16. So doing 4 lots of this bracket, 16 plus 8 √3. Then do 2 √3 lots of the bracket. So we get another 8 √3. 2 √3 times 2 √3 is 12. 4 times 3 is 12. So it becomes, what is it going to be? 28 plus 16 √3. Divide by the 4 because you've got quarter, so you get, what do we get? 7 plus 4 √3. Okay, and don't forget about -4. -4 at the 7 is going to give me 3 plus 4 √3. That should be my final answer in the correct form. A plus B √3. So A is 3, B is 4. That should be correct. Yeah, there we go. Okay, so look at another question. So question 6. She says show that sine 5x equals sine of x minus 2 sine x cos squared x plus sine x cos squared x. Now obviously we're probably going to use the reverse chain obviously to integrate that function then. Okay, so the only way we're going to do this then is obviously we've got sine 5x, which is going to be sine x, sine squared x, sine squared x. Yeah, so we've obviously got cos because of the cos 4 there. So this is sine of x, change to 1 minus cos squared. Yeah, do it this way. So you get sine of x. So one lot of that is obviously 1 minus cos squared x. Then when times by minus cos squared, we get another minus cos squared, and we get a plus cos 4, don't we? You see? So then if we multiply through, we've got sine of x on this term. We've got minus 2 cos squared times that is going to give me a minus 2 sine x cos squared x. And our final term will just be sine of x cos 4, which is what they've asked us to show. Then going to use reverse chain rule to try and integrate this, but we're going to integrate it separately. Sine of x cos 4x, yeah, that makes sense. Okay, that's fine. Okay, so let's try and integrate this function now then with respect to x. And obviously what we're going to do is we're going to do this separately, and we'll need to use the reverse chain rule on the second and third integrals. So think about it like that. You see? Okay, makes sense because we know that sine of x will just go to minus cos of x. We've got minus cos of x here. And then obviously what we've got is we've got minus integral 2 sine x cos squared x plus integral sine x cos 4x. Okay, so this is using the reverse chain rule, the rule that we used previously on the previous question, where we've got the integral of k f dash x f of x. It's a pair of n dx. Okay, so if you look at our first integral, we've got integral of 2 sine x cos squared x, haven't we? Yeah, dx. So clearly our f of x, our function, is the one with the power, so it has to be cos of x. So again, we first do our f dash, which is going to be minus sine of x. Yeah, okay. So what we've got a pair of two, so we know we're going to get cos cubed x in our integral. And what do? We're going backwards, remember? Reverse chain rule. So we're thinking what that goes to. Well, when we differentiate, the 3 obviously will come down. The cos will differentiate to minus sine. And then we're just left with, knocking off the pair, we've got a cos squared. Okay, so again, we know that minus 3 sine squared x, apologize, minus 3 sine x cos squared x, that will integrate to cos cubed x. We know that, don't we? Okay, well, look what we've got. Look, so we've got 2 sine x's on the constant 2, rather. Where we need a minus 3. Can you see we need a minus 3, not a 2? Okay, this is where our adjustment constant comes into play, doesn't it? Okay, so what we need our integral to be is we need minus 2/3 integral minus 3 sine x cos squared x. Can you see? Because minus 2/3 times minus 3 gives me the 2, what I've got. So again, just checking that this is the same as this, which it clearly is. Yeah, that's the whole point of this. Our adjustment constant, our k is minus 2/3. Yeah, so we can therefore say that this integral must be minus 2/3 cos cubed x. Let's make that a bit neater. Okay. So then this becomes minus cos x. Now remember, we had a minus outside, which didn't account for. So it's going to be minus minus is plus 2/3 cos cubed x. Yeah? Let's make it a bit neater. Plus 2/3. Okay. Yeah, so minus cos x plus 2/3 cos cubed x. Now we've got to deal with a third integral. Okay. Let's make some room. Yeah, make some room. Right, so now what have we got? We've got the integral of sine of x cos 4x. The x. Okay, so again, cos with the power, so let's make a note. So our function has to be cos of x. We know f dash x is minus sine of x. Okay, and we know our integral has to have cos 5x in it, doesn't it? Because add 1 to the power. Yeah, so a reverse chain rule. So we differentiate to go back to what we need. So the power comes down 5, cos goes to minus sine, and then we knock off the power, we've got our cos 4. Can you see? So again, we know that if we integrate the function minus 5 sine x cos 4x, we integrate it, we're going to get cos 5x. So we need that function in our integral. That's what we need. Well, a bit neater, it is a 5. Yeah. Now, again, looking what we've got. So we want minus 5 sine x. We've just got 1 sine x. Okay, so what do? We use our adjustment constants. We know, quite simple, this one, so minus a fifth of minus 5. Minus a fifth of minus 5 is simply 1. So minus 5 sine x cos 4x. We know we'll go to minus a fifth cos 5x. Can you see? So that's our integral. So I'm going to put that there. So minus a fifth cos 5x, and then just finish with the plus c. That should be my final answer. Part B. So minus cos x plus 2/3 cos cubed minus a fifth cos 5. Let's see. Yeah, perfect. Minus fifth cos 5 plus 2/3 cos cubed minus cos plus c. Perfect. Okay, so last question then, looking at one with a fraction, obviously. So we're using, remember what I said before, we use now one when we've got k f dash x over f of x dx. This is the version we're using for this one, okay? Makes sense. So our key function is what's on the bottom. So our key function is that x squared plus 3. So that's going to obviously be our f of x. So if we just make a note that change the pen. So f of x is our x squared plus 3. Yeah, we know that f dash x, quite simply, 2x. So what we need that 2x on top. We've only got x, so we use our adjustment constant will clearly be a half. So we're going to do a half integral 2x. There's a half to x, which is x, what we've got, yeah? Our adjustment constant k is half over our x squared plus 3. Okay, dx. Can you say? So this is our half. Makes sense? F dash x over f of x dx, which will go to half ln, natural log, f of x. Put our f of x back in, is a half natural log of x squared plus 3. That's the way it works. Between the two limits, k and 1. We know what the answer is going to be, don't we? We're going to equate them. So let's put our k in first. We've got a half natural log of k squared plus 3 minus a half natural log, well, 1 squared plus 3 is 4. Now log laws, because we've got the constant being the same, we can use the division law. It's fine. So we've got a half natural log, and it's going to be k squared plus 3 all over 4. Like so. And they're telling us that equals natural log of 3 over 2. Can you see it? So what you need to do is obviously bring the half in, power law, we'll bring it in. So what we've actually got is natural log square root k squared plus 3 over 4. Can you see? Equals natural log of 3 over 2. When you get to that point, you can just cancel the logs quite simply, because yeah. Then we're going to then we can square both sides. So we've got k squared plus 3 over 4 must be equal to 3 over 2 squared, which is simply 9 over 4. Change that to 9 over 4. Cancel the 4s. Take off 3. So I know that k squared 6. So k should simply be root 6. Check that. Yeah, there's your root 6. Okay, so hopefully that's explained the reverse chamber with three questions from the practice book. Thank you.